Good afternoon, everybody, and welcome to my presentation on driving the electric revolution safely and securely. It's a pleasure to be talking to you at the Powertrain Technology Conference this year, and I hope I'll be able to give you some great information. So I think the title here says everything, but you know, there are some real challenges facing everybody in the industry because the 2030 ban on the sale of new diesel and petrol vehicles has really focused everybody's mind and is really not very far away at all. So, if we just move on just a little bit about me, I'm a compliance expert. I've been 26 years actually now with TUV SUD in the field of product testing and certification. I won't bore you with all the details, but I am experienced in battery safety testing, and I'll talk to you a little bit about that as we go through the presentation this afternoon. So, I just wanted to kick off by looking at the setting the scene, really, looking at the overview and the big picture. I've just cobbled this graph together, so please don't take it as gospel, but what is pretty clear is going to happen is you can see on the red curve here that internal combustion engine propulsion is going to rapidly diminish down to very, very low levels. Electric vehicle propulsion, on the other hand, is going to mirror it in the opposite direction and become very, very widespread and commonplace. And then in grey, I've just shown what I think is going to happen with hybrid electric vehicles. I think there is going to be a peak towards 2030, and then we think there is going to be a tail off after that. And of course, just to reiterate, we have this 2030 UK government target to ban the sale of new petrol and diesel vehicles. And there is a real move, if you have a look over on the right hand side of the slide, towards CASE, connected, autonomous, shared and electric. And I think that's the way that everything is going to start to transition very, very rapidly. And I've just taken some statistics here. Some of them are a little bit out of date. It doesn't really matter, but if you have a look at this bottom graph here from the International Energy Agency, it's just really to show you the exponential growth that we have in electric vehicle deployment and use. And if you have a look at the numbers, we have around 495,000, so just under 500,000 electric vehicles currently in the UK, and we can split those down: 235 fully electric, 260,000 plug-in hybrids. And we've got over 23,000 public charge points, so there is real momentum building here. So we're making good progress, but nonetheless there's still a long way to go to meet that 2030 target. And I just wanted to take us back a little bit and look at electric vehicle car development versus internal combustion engine. So if you look at internal combustion engine development, we've had 120 years of vehicle development. You compare that to 25 years of viable electric car development. So electric cars have actually come around very, very quickly. So in 1996 we had the EV1, Toyota Prius in 97, 2006 the very famous Tesla Roadster, 2011 the Nissan Leaf. I can't believe the Leaf's been with us since 2011. But we've seen an increase in technology, starting with lead acid, nickel cadmium, nickel metal hydride, up to lithium ion, which has enabled us to get to where we are today. And there are some key drivers that I just wanted to talk about. So this is cost per kilowatt hour is coming down and needs to come down. On the other hand, energy and power density, safety, first life, so what I mean by that is acceptable service life, temperature, predictability, so predictability in terms of performance and aging, all need to be increasing. The bottom point, and in red, I'll talk a little bit about more in a second, but recycling percentage by weight needs to come down. Recycling by precious minerals needs to go up, and I'll tell you what I mean by that in a second. The challenge here is that it takes 10 plus years to take a new chemistry from concept to production, so we're not going to have that for 2030, but what we are going to see are advances in the current lithium-ion technologies. And if we just look at batteries versus fossil fuels, if we look at energy, so batteries comparatively low compared to fossil fuel, power on the other hand comparatively high compared to fossil fuel. Batteries very efficient, we've got high voltage to increase efficiency, so the I2R losses are quite low, and energy transfer from batteries is very efficient. much more so than fossil fuels and internal combustion. But there is a public trust issue here, and if we look at fossil fuels to start with, what we do know is there are risks in life with everything. There is a risk in getting in an internal combustion engine vehicle. We're putting flammable fuel in a fuel tank, and we have electricity and ignition sources and other sources and crash risk and everything else. But actually, the public have developed trust over that time despite the well-known and accepted risks. I just wonder actually today, if we were doing a risk assessment on the internal combustion engine vehicle today, whether it would actually have got off the drawing board. But as far as batteries are concerned, there is a perception issue. There is a lack of trust. There is definitely range anxiety, and the whole technology is new and relatively unknown. We just looked a few slides ago at 120 odd years of internal combustion engine development, 25 years of battery development. So what happens if you crash? And development of automotive batteries, I just wanted to follow that across. I won't go through the whole slide, but I just wanted to follow through from lead acid to lithium ion. So lead acid, advantages, cheap and widely available, disadvantages, low energy density. And then we saw a gradual increase in the advantages. So NiCad to nickel metal hydride, energy and power density increased, cycle life was good. There were some disadvantages. Lithium ion, though, widely credited to the gentleman shown in the bottom of that slide, we get a high energy and power density, high efficiency, grid to wheel efficiency, at least 60%. But they do need careful management and handling, and we'll come on and talk about that in a second as we go through the presentation. But before we do that, let me just go back. I just wanted to talk about raw material security, recycling and second life applications. So you can see the source of this report, but what I really wanted to highlight here is this looks at resilience of the supply chain. We're not talking about wind or PV today, so it's just the bottom curve that we're interested in here. But if you look at where we were in 2015, cobalt and lithium were at medium risk. Those other materials were in the red zone, so that's not good. If we don't do anything with no mitigation, everything falls into the red zone. So that includes cobalt and lithium, critical in the production of lithium-ion batteries. If we do take mitigation measures, and I'll tell you what I mean by those in a minute, then it doesn't fix everything, but it makes the whole outlook much better. Certainly, lithium improves, cobalt improves, other things improve. So while there is work in hand to reduce the reliance on those materials, we do need to do something about it. And you would think that the EU battery directive would do something about this, because it says that you have to recycle 50% by average weight of the waste batteries and accumulators. But actually, that's a really, really easy and very soft target, because to get 50% average by weight, you can recycle the easy stuff, the carbon, the aluminium, the iron, the manganese, none of the critical elements. And actually, recycling the critical elements is very difficult, very time consuming, and as such, very expensive. So we need to get better at recycling. Second life applications could be part of that solution. So typically in an EV application, you can no longer use a battery effectively when they fall below about 80% capacity. We've already established recycling is difficult and cost prohibitive, but second life applications could be the solutions, but there are challenges to that. So it's difficult and time consuming to validate used battery packs, battery modules and cells. You don't know the history. They've been in a vehicle or several vehicles maybe. You don't know how they've been used, what temperature, what conditions they've been charged and discharged in. And the existing battery management system, we'll talk a bit about battery management systems as we go, may not be suitable for their new second life. And typical second life applications are off-grid energy storage. Just because a battery is 80% capacity certainly doesn't mean it's no good for anything else. And actually there's a news article I've included here where there was some work that Warwick University did in conjunction with Nissan, where they actually came up with a safe, robust and fast methodology for grading used automotive lithium-ion batteries at pack level. So there is work and it is progressing in this area. So cells, modules and packs, these are our building blocks when we go to make an EV, electric vehicle battery pack. Types of battery cell, you will generally find three. Cylindrical on the left, prismatic in the middle, and pouch design on the right. No particular advantage or disadvantage to each, it just depends on what the battery pack manufacturer or the vehicle manufacturer decides to use. But cylindrical, prismatic and pouch. Pouch cells you can fairly well recognise because they look like foil packets. So, single cells are, as I said, cylindrical, pouch or prismatic, and they are low voltage. They're the fundamental building blocks. You take those cells, you connect them together in series parallel configuration depending on what voltage and current you want ultimately, and you put them into what we call a module. And that module provides mechanical support, thermal management, electrical interfaces so you can connect these modules together. Then you connect the modules together and you form the pack. So we go from cells to modules to a pack. Modules are relatively high voltage, packs are very high voltage such that it will kill you if you get it wrong. And of course you have an energy hazard relating to that as well. So packs are constructed by connecting the modules and by adding sensors and a battery management system. And they may well actually form part of the vehicle structure or the crash structure. So that's why you might see some odd shapes and designs for battery packs. So in a module, you'll have a case, you'll have battery cells, you'll have temperature sensors typically that feed back to the battery management system, you'll have terminals, and you'll have cooling channels, either for air or liquid cooling. In a pack, you'll have a case, upper for fire and ingress protection, lower for mechanical support and protection from damage. If it's part of the vehicle chassis, it's going to be subjected to some quite nasty surprises potentially. Of course, it has the battery modules, it has buzz bars for interconnection, fuses, disconnection, cooling, air or liquid, and the battery management system. And it's the pack that is the overall finished product as far as our EV battery is concerned. There's a few key design tips that you can take here. Use physical partitions and fire breaks to minimise fire propagation. Good thermal management, getting rid of the heat and keeping the battery at good temperature. You know, battery packs are very similar to us humans. They like to be at about the same temperature that we are to operate safely and effectively. Use pressure vents, relief mechanisms to deal with external pressures. Utilise sensors and the BMS to identify abnormal behaviours. We'll talk about that in a second. And use materials for the foreseeable temperatures. Of course, if it's a vehicle, it might be used in a hot climate, might get wet, you know, you don't know. And use constructions appropriate for the real world. So you've heard me talk a little bit about battery management systems. Well, they have two main functions. One is a hardware provided functionality and one is software. We'll talk about software in a minute, but hardware is typically current sensing. So this is for state of charge estimation and for safety. Pre-charge circuitry, this is so that when what you don't want to do is energize a big contactor and have a huge inrush current to deal with, so this is like a soft start circuit. Leakage current, so what you don't want to do is have a risk where that high voltage in the battery could appear on the vehicle chassis. That would obviously be very bad. Relays, contactors and so on for disconnection, and fusing for safety and overcurrent protection. Software generally provides interface and comms to the vehicle CAN bus. Diagnostics and health, state of charge and state of health. State of charge is important for control and safety and for range estimation. State of health determines battery degradation over time and cycles. And it also provides control, electrical isolation, thermal management, charge, discharge, cell balancing. Cell balancing is quite critical. And what might well be the case is you might well find that these battery management systems become connected batteries. So you might have data over the air. So you could have near real-time data to optimizing charging and discharging. So if you're in a very hot climate, then it might change the algorithm to improve the performance of the battery pack. Predictive maintenance and failures, remote troubleshooting, analytics using big data, software over the air. So on-the-fly software updates to deal with aging and extreme operating conditions. You know, I touched on that a minute ago. And 5G clearly will be a driver to facilitate that, but then of course you've got the regulatory and data security and data privacy elements behind it. So testing. let's have a quick think about testing and where we go. So you can break testing down a little bit here. There's robustness, so things like temperature, hot, cold, humidity, solar, snow, icing, salt. Dust, ingress protection. Water, again ingress protection, but dripping, splashing or submersion. Shock and vibration, high frequency, high amplitude is not going to be unexpected in an electric vehicle. And you're likely to have impact. What happens in a crash? Fire resistance and flammability. Then you have transportation tests. Batteries are classed as dangerous cargo. Mechanical tests, electrical and thermal tests, all covering abuse and electromagnetic compatibility. So we'll look at each of these aspects as we go through. But first off, I probably don't need to tell you this, but battery testing can be dangerous, and I'm sure some of you will remember, or all of you will remember, the fire triangle, that you need to have some combustible material and some oxygen and some heat and energy to make fire. If you don't have one of those, you're not going to get fire. Well, the good or bad news is, whichever way you look at it, is you do have combustibles, so you have lithium and dendrites, the solvent and salts, the gases. You have oxygen that can be released from the cathode, but also if the cell is exposed in a crash or as a result of a rupture, then you have oxygen coming in. And of course you can have heat or energy, anode or cathode decomposition, or a short circuit of the cell, internal or external. So it's really critical, I won't talk through all these points, but it's really critical that you understand and have safety data sheets and health and safety information which cover all of these things that you have on here. So, potentially dangerous constituents, nature of the chemical risk, firefighting measures, handling and storage, and certainly if you go to a lab for testing, the lab's going to want to know and is going to ask you for this information. The drivers behind cell failures, we can start to break these down. So you've got overcharge and discharge, consequences of repeat overcharging, metallic lithium plating, metallic copper plating, so this is just effectively unwanted electrical paths in the battery. Instability, a short circuit that grows, and it certainly can be accelerated when cell defects are present. Overcurrent and high temperature, well, excessive ionic flow damages the crystalline structure of the cathode, raises the temperature, can ignite the electrolyte, not self-extinguishing. And low temperature, if you charge at low temperature, you can get metallic plating, instability through short circuit. So cells, well, these are especially sensitive to mishandling, improper packaging, deformation and contamination, particularly pouch style cells, these foil cells I told you about. The cylindrical cells and the prismatic cells have some much better rigidity to them, but certainly all the cells suffer these to some degree, so you have to be careful with them. And what you also need to be thinking about here is beyond the data sheet. So it's pretty clear. In the green zone, we expect safe operation, no cell failure. And likewise, in the red zone, the abuse zone, we also expect, a clear outcome. We expect cell failure. But there is a grey zone. And this grey zone, what happens if we push the boundaries a bit? So what happens if we exceed the recommended charge-discharge rates, exceed the recommended temperature envelopes, exceed storage, go below minimum state of charge, and so on? So this grey area here that we're talking about is actually very, very important for us. So I spoke a bit about abuse testing. Well, you have mechanical abuse testing, and it sounds great when you go through this stuff, but you have what is very, very, sounds very impressive, a nail penetration test, and it's exactly what it says. You get a sharp steel rod and you puncture it through the battery, and it simulates an internal short circuit. So it compromises the integrity of the separator and the electrodes. There are questions over the usefulness of this test and the repeatability. You can repeat the test several times and get different outcomes, but it is an accepted test methodology, nail penetration. Crush and indentation, so you'd either get a hemisphere or a semicircular bar, and you would force it onto the battery to deform the battery enclosure, so you'd apply a reasonable amount of force at this point. Again, you're trying to replicate short circuits and failures. Vibration, we want to know what the tests of long-term vibration are. Sine and random profiles are used, but battery packs are going to be subject to vibration. Drop, this could happen during removal, installation of a battery pack, or other activities perhaps. Shock, replicates sudden acceleration, deceleration, curb impact or crash. So you can relate all of these tests back to the real world conditions. And immersion, what happens if you get partial flooding, so a coolant leak, for example? What happens if you drive through a ford, and the thing gets wet? So typically salt water is used, although you may use other liquids. So quite harsh tests that you put this stuff through. And just a word of caution is on abuse testing, you need to be thinking with the safety of the lab in mind as well, and of course for you guys. If you take a battery, it's always good practice to think, well, do I need to do all of these tests at 100% state of charge? Could I do some at 0 state of charge, or 25% state of charge, or 50% state of charge? If you reduce the state of charge in the battery, you reduce the risk. So it's just worth thinking about. Of course, some tests can only be done at 100% state of charge. Electrical abuse. So we have electrical short circuit. You apply a low resistance to the tabs to verify the ability of the cells to withstand the current. Just a quick note of caution here, though, is you've got to make sure that not all short circuits are the same. You've got to make sure it's a controlled, verifiable short circuit. So a nice low impedance. You've got to pay attention to wiring and test setup here. An internal short circuit. Introduction of a metallic foreign object inside the cell. Standardization methodology is being developed for this test currently, but there is the test to look at that as well. And overcharge and over discharge. So charge at a specified C rate beyond recommended limits. So charger failure, for example. Discharge at a specified C rate to a required state of charge and hold it. So, in both those cases, you can end up with some hazard. And thermal abuse. So thermal shock, the battery is exposed between two temperature limits and held for a specific period of time. You really want to shock the battery between the two, so you don't want to let it, cool down or heat up slowly. You want to shock it between the two extremes. Thermal cycling, temperature cycle at a specified state of charge between temperatures defined by the manufacturer. And then high temperature endurance. So for example, 130 degrees C for 30 minutes. And electromagnetic compatibility. I don't know how familiar everyone is with this, but effectively electromagnetic compatibility is the ability of something to operate as it's intended in the electromagnetic environment that it resides in, and not to be interfered by other co-located equipment. So a battery management system has a lot of electronics in it, so it needs to be tested, and I've suggested the industrial generic standards here, but particularly for the BMS, but you need to be making sure that that battery pack and particularly the BMS is resilient, that if you use your mobile phone in the car, that you're not going to upset the operation of the battery management system, because that would clearly be very bad. And then there's transportation tests. So lithium batteries are designed, lithium-ion batteries are classified class 9, miscellaneous dangerous goods. There is a test standard, UN 38.3, has test T1 to T8, altitude, thermal, vibration, shock, external short circuit, impact, overcharge and forced discharge. If you don't have evidence of these tests, you're not going to be able to ship your batteries. That's clear. So all of the carriers are going to want to see some evidence that those tests have been carried out. I'm starting to come to the end of this, but I did just want to also talk briefly about high voltage safety. So anyone working with high voltage systems must be aware of the potential dangers and protective measures. Battery modules can easily operate above 50 volts DC. Anything above 50 volts DC is starting to get into danger levels. Battery packs are operating at hundreds of volts DC at a lot of current. So this applies to really anyone who comes into contact with these things. So employees, mechanics, technicians, cleaning staff, office workers, anybody who's going to come into contact with these vehicles and these battery packs. And the electrical hazards we're talking about here are electric shock, arc flash, heat wave, fire burns, explosion, shrapnel, hot molten metal. These are not things to be messed about with. So working with high voltage DC modules, packs and cyclers requires expert training, certainly personal protective equipment, specialised first aid equipment and specific health and safety measures. So, it's always good to seek some independent training for your people if they're going to be involved with these systems. And I just wanted to round off by taking a very, very quick look at hydrogen fuel cells, and I'm going to leave everybody with a question. And my question that I'm going to pose to everybody is the future batteries, or is it a hybrid approach using the benefits of both battery and hydrogen? Hydrogen fuel cells clearly have a place for commercial vehicles. I just wonder whether, my own thoughts, my own musings here a little bit really, but I just wonder whether, if you look at the benefits of hydrogen fuel cells, they take away some of the negatives about batteries. If you look at batteries, they take away some of the negatives of hydrogen fuel cells. So maybe there is a place for hydrogen fuel cells for greater applications outside of hydrogen buses and trucks and so on. And a hydrogen fuel cell, if you don't know, it's just an electrochemical cell that converts energy of hydrogen fuel into electricity. They're safe, they're functional, they're efficient fuel cells and infrastructures, critical for transition to sustainable energy. I think, I've posed that question to you, but I think, yes, actually there is a place for this hybrid approach, but you need to consider testing and certification, and again, safety training. Different kind of safety training. This time it's handling of gases and liquids such as methanol, hydrogen, natural gas, liquid gas, and so on. And that brings me to the end of my presentation on electric vehicles. So we've to recap, we've looked at, set the scene, looked at a bit about the future, what's going to happen in the next 10 years and beyond. We've seen the development, we've spoken a lot about testing and some of the pitfalls and some of the risks with the technologies. We've looked at the issues around recycling and second life. And then we've ended up just talking a bit about high voltage safety and whether hydrogen fuel cells may have a complementary place to add in the scheme of things. But I hope you've enjoyed that presentation, and thank you very much for listening.